Hello, welcome to another video of sectoral structures theory. We started talking about the boundary of a sectoral structure in our last video, and today we will talk a little bit more about the boundary of sectoral structures. So again, this is all part of the chapter that is focused on sectoral structures theory from the perspective of graph theory with some adjustments. In this chapter, we will combine several concepts we have seen before. It's pretty straightforward. We have previously seen what isomorphic sectoral structures are. Basically, two sectoral structures are isomorphic if they can both be reduced to the same sectoral structure. So if you remember, we said before that the dal, this dal letter before the sectoral structure, it indicates the reduction of a sectoral structure to its irreducible form. So if two sectoral structures can be reduced to the same irreducible form, then we say that the two sectoral structures are isomorphic. For example, we have AN equals 2, 1 subscript 3, this one here, and we have BM equals to 4, 2 subscript 6, shown here. If we take the dal function of both of these, dal of an gives us the same thing, an, and dal of bm is reduced to 213. So they are both reduced to the same sectoral structure. Therefore, we say that an is isomorphic to bm. Now, we want to use the definition of the boundary of a sectoral structure. We've seen earlier that the boundary of a sectoral structure is basically the union of the curve of that sectoral structure and the walk of that sectoral structure. So for example, here we start at the two delta joints. So we're going to draw the curve and then the walk, and they give us this enclosed space, which is the boundary, or the outside is the boundary of the sectoral structure. But also notice that the boundary is a closed space or forms a closed space. Now, we also saw earlier that the boundary doesn't have to be obtained from the walk and the curve. It can be obtained from any two trails that are complementary to one another. So we've seen that before. So let's look at, for example, if we take this trail here, and in trail notation, starting from here, we will say that this is an this is an OX trail, and the complementary one will be the XO trail. So this will be X, and this will be O, and together they give us an enclosed space which forms the boundary. So if two sectoral structures have the same boundary, then the two sectoral structures are isomorphic. So this is another definition that we can use for two isomorphic sectoral structures. We couldn't really use it earlier because we hadn't defined the boundary yet. Conversely, if AN is isomorphic to BM, then the boundary of AN is identical to the boundary of BM. Similarly, if we take all the trails of AN and all the trails of BM, and the two are isomorphic, then they will have the exact same trails as well. So not just the boundary, but the full list of trails will be identical. So we will say Tx, where x is any number between 1 and 2 to the power of lambda. So Tx of an is identical to Tx of bm. And that's basically for isomorphic sectoral structures. Now let's look at a more interesting case for the boundaries of two conjugate sectoral structures. So if you remember, we said we form the conjugate of a sectoral structure by turning every beta joint in it to an alpha joint. So here we have two betas, here we have two alphas, and turning every alpha joint into a beta joint. So for example, the sectoral structure 1, 2, 1 subscript 4 has a conjugate 2 squared subscript 4. So let's see what we can learn about the boundary of these two conjugates. Clearly, they are not identical, as we can see just by looking at them. But we know that the boundary of an is equal to the walk of an plus the curve. And we know that the walk of an, or the walk of any sectoral structure, is 2 times lambda, or 2 times its order. So let's say delta, or sorry, the boundary of an is equal to 2 lambda plus 2 pi. So that's the walk plus the curve. And similarly, we can say that the boundary of the conjugate of an is equal to the walk of an plus the curve, which equals to 2 times lambda bar. We'll put this bar to indicate the order of the conjugate, plus 2 pi. We can see just by looking at these two, we can see several things. For example, if we subtract these two equations from one another, what we get is that the boundary of an minus the boundary of its conjugate is equal to 2 lambda minus 2 lambda bar. So the 2 pi's cancel out, and we're left with the difference between the walks of the two sectoral structures. We know that we've seen earlier when we looked at the beginnings of the graph theory for sectoral structures that the order lambda of a sectoral structure plus lambda bar, which is the order of its conjugate, is always equal to n plus 1, so the degree plus 1. Let's double check. Here we have a sectoral structure of order 3. We're going to add it to its conjugate, which is order 2, so that's equal to 5. N in this case is 4 plus 1 is 5. So this is just an example to confirm it. Let's multiply this by 2, see what we get. We get 2 lambda plus 2 lambda bar. This is the same as saying 2 lambda is the walk plus the walk of the conjugate is equal to 2n plus 2. So we have these two equations now. We're going to combine them together. We're going to add these two equations, and this simplifies to the following. 4 lambda, because the lambda bars cancel out, equals to the boundary of an minus the boundary of its conjugate plus 2n plus 2. We're going to solve for the boundary of the conjugate. We will say that the boundary of the conjugate is equal to the boundary of an plus 2n plus 2 minus 4 lambda. So what does this mean? This means that if I know the boundary of a, let's say we have a complex sectoral structure of degree 100 that's very difficult to deal with, and we want to figure out the size or the length of the boundary of its conjugate, all we have to do is find the length of the boundary of the sectoral structure and then add 2n minus 4 lambda plus 2 to it. We can express this in another way. It may not be more useful, but it's also a simple way to look at it. We know also from earlier videos that n minus lambda is equal to the number of alpha joints. And we know that lambda minus 1 is equal to the number of beta joints in a sectoral structure. So we can simplify this equation into the following. The boundary of an is equal to the boundary of an plus 2 alpha minus 2 beta. So that makes it really easy if we know alpha and beta. Let's take an example to confirm this. So we have these two conjugate sectoral structures. Let's calculate the length of the boundary here. That would be 2 pi, which is the sectoral curve, plus 2 times lambda, which is 3 in this case. So 2 times 3 is 6. So 2 pi plus 6 is the so that is the boundary of an. So according to this equation, the boundary of its conjugate should be an, which is 2 pi plus 6, plus 2 times n in this case is 4, 2 times 4 is 8, minus 4 lambda, lambda is 3 times 4 is 12, minus 12, plus 2. So this simplifies to 4 plus 2 pi. This should be the boundary of conjugate an. Let's double check. This is 2 pi, and then we've got two parts, or two parts. So the order is 2. 2 times 2 is 4, and that is correct. That is what we have here. Let's use the other equation. So 2 pi plus 6 plus 2 alpha. We've got 1 alpha here times 2. That gives us 6 plus 2 is 8. Minus 2 beta. 1, 2 times 2 is 4. 8 minus 4 is 4. So we get the same result twice. Thank you very much.